Okay, I'm going to talk about heating curves and energy changes. So, um, heating and cooling curves, usually we just call them all heating curves, give us a representation of how temperature and heat are related for a sample. And when you add or remove heat from a sample, it can cause temperature changes, but it also can cause phase changes. So on your heating curve, you'll see some regions where the curve is sloped. Okay, so you have some slopes, you actually have a temperature change as heat is either being added or removed. But then some regions it's completely horizontal, it's just flat. And those are the regions where you have some change in the physical state of the substance. So a heating curve or a cooling curve helps you to kind of break down the energy associated with that process. Um, and we can actually quantify the amount of heat associated with each segment of the lines in your heating curve or in your cooling curve. And so let's talk about how we would quantify that information, because it's not always given the on the actual plot. Sometimes they just give you a little bit of a generic plot where there's no numbering on the axis. Um, so we're going to talk about the different energy calculations when you have temperature and phase changes, or specifically you're calculating the heat. That's the type of energy we're calculating. Um, so first we'll look at the energy associated with a temperature change. So when the temperature of some substance changes, that amount of heat associated with that temperature change is always related to a heat capacity. And so you've got a couple ways this relationship could be written. One way is Q equals MC delta T, and I have it labeled as CS. It can just be C. Some people use the letter S instead. Um, but basically the Q is the heat, and so that's the amount of energy. The M is the mass of your sample. The CS is the specific heat capacity of that sample. And so that's going to be directly tied to what substance you have and what physical state it's in. And then you have the delta T, which is the change in temperature. And so that's TF minus TI. And that part, you can plug that part in degrees C or in Kelvin, and the change in temperature will come out the same. Um, Whereas the mass, you need to match its unit with the heat capacities units, which usually are on a per gram basis. So you usually plug in your mass in grams. Now, you sometimes see this relationship written in terms of moles instead. Um, and so it could be written as Q equals N C delta T instead of M C delta T. Um, and really, the only reason that sometimes it's written that way is if you have what's called a molar heat capacity. So instead of a specific heat capacity, which is on a per gram basis, a molar heat capacity is on a per mole basis. So you would multiply by moles instead, but the rest of the equation is the same. Um, and so you can quantify the heat associated with any temperature change if you know how much sample you have and the heat capacity of that sample. Okay, so that would be for any temperature change. But remember, the heat capacity is specific to the substance, but also to the phase of the substance. So if you're dealing with that substance and at some point it changes phases, you would actually have to do two separate calculations for the different phases because the heat capacities will be different, and then you would just sum those heats together. Okay, now if we want to quantify the heat associated with a phase change, then what we need to be dealing with instead of heat capacities are what we call enthalpies. So you can have, or you can look up an enthalpy value that is an enthalpy of vaporization, or enthalpy of fusion or enthalpy of sublimation. So those all relate to phase changes. Okay, so enthalpy of vaporization is associated with the transition of a liquid to a gas. Okay, whereas fusion is for a solid to a liquid and sublimation is a solid to a gas. So those values tell you how much heat it takes to change the phase of a given amount of the substance. Okay, now sometimes people will call these values heat of vaporization and heat of fusion and heat of sublimation, and that's fine instead of enthalpy. And let's see, notice that there's only 3 of them given, but there's 3 other phase changes, but those phase changes are just the reverse. And so the amount of heat associated with the process is the same magnitude. It's just designated as an opposite sign because the energy would be going in a different direction. So these are all the endothermic processes. So your enthalpies of vaporization, fusion, and sublimation are positive values. So when you use them in the calculation, the heat comes out positive, meaning that that sample absorbs that much heat. If you were talking about the reverse process, you would just change its sign to a negative, and that would indicate it is releasing that much heat. So you can write out the calculation kind of as an equation, just like the temperature change equation, but it involves the delta H. And so with that, it'll just simply be a number of moles, so N times delta H, okay? Or most often, this is the most common. Most of the time when you have these enthalpies, they're given in units of kilojoules per mole. Occasionally they're given in like kilojoules per gram. If that were the case, you would multiply by grams instead of moles. But the majority of the time they're given per mole. So that's why I write the equation this way. But basically you need to get it down to an energy. So you're going to multiply by that number of moles in order to cancel out the moles. And so you can use that to quantify the energy to change the phase of a substance. And so all it depends on is the enthalpy for that transition for that substance and how much you have. Now, just like heat capacities, these enthalpy values are specific to the substance. So the enthalpy of vaporization of water is different than the enthalpy of vaporization of, say, benzene. Okay, so they're different substances, so it takes a different amount of heat to cause that transition. So you can put all of this stuff together if you have a multi-step process where you have temperature changing and then phase changing and then temperature changing again. You would just have to do multiple calculations and then just add them together. So we're going to do some examples. So this first one, I give you a heating curve for it to show what I'm wanting to know. But it says calculate the heat required to convert 15 grams of ice at negative 10 degrees C to water at 35 degrees C. Okay, and I give you the specific heat of ice, the specific heat of water, and the enthalpy of fusion of water. Okay, and remember, ice and water, that's all H2O. Okay, it's just when we call it ice, we're talking about it in the solid phase, and when we call it water, we're talking about it in the liquid phase. Okay, and so that's kind of what's shown on this heating curve is we're starting at negative 10, so this is our starting point, and then we want to heat it up to 35 degrees C, okay, which at that point it's going to be water, so this is our ending point. And so based on that heating curve, the different segments, you can quantify those heats by themselves and then sum them together. And so from this first point to here, that's our first step. And in that first step, what we have happening is we have negative 10 degrees C ice, and we're going to 0 degrees C ice. Okay, because once we reach 0 degrees C, we're actually at the melting point. Okay, and then the next step, we're going from our 0 degrees C ice and we're adding heat, and that is a phase transition, that flat point. And so at that point, that step 2, is going from 0 degrees C ice to 0 degrees C water. Okay, and so we need to quantify that next. And then our third step, we're again increasing the temperature. Okay, so we're going from 0 degrees C water to 35 degrees C water. Okay, so those 3 steps, it's jumping between temperature and phase changes. So the first one is a temperature change. Okay, and since it's temperature change, we use Q equals mc delta T. And then the second one's a phase change. So we're going from the solid to the liquid. And so that one we need to use the enthalpy value. And then the third one's another temperature change. So another mc delta T calculation. So let's write down the work for these. So the first one's a temperature change. So Q would be equal to my mass, which is 15.0 grams, times the heat capacity, which this would have to be the heat capacity of ice, since that's the substance, that's our solid water. Okay, so it's 2.10 joules per gram degrees C. And then I take my change in temperature. So my final 0 degrees C, and my initial is negative 10 degrees C. Okay, so I'm taking 0 minus negative 10. Okay, and that 0, that is the freezing point of water or melting point of water, so that's exact. Okay, that's not going to affect my sig figs. So we could go through and calculate that, and we would have, let's see, 15.0 times 2.10 times 10.0. And so that gives us 315. And if you look at your units, the grams cancel, the degrees C cancel. And so that gives us joules. Okay. And then let's see, our next step is a phase change. We're going from ice to water, or solid H2O to liquid H2O. So then our Q is going to be equal to our moles times that enthalpy, because the enthalpy is given in kilojoules per mole. And so I have my 15 grams, and remember that's H2O, so it can be helpful to write that. And I need to get that to moles. And so I can cancel grams of H2O and go to moles, H2O, by using the molar mass. So if you add up 2 hydrogens and an oxygen, you should get 18.02, at least to 2 sig figs, and then multiplied by that enthalpy value, 6.02 kilojoules per mole. So, oops, let's see what that gives us. 15.0 divided by 18.02 times 6.02, and that gives us 5.0. Now the one, I wrote it down as 315. I think that came out exact. Okay, and that is the correct sig figs 3. But this next one, it should be 3 sig figs, but it gives me more, so I'm going to go ahead and write an extra while we're at it. And that's going to come out in kilojoules, okay, as the grams cancel, the moles cancel. And then we'll do the last one. The last one's a temperature change. And so that one, our Q is going to be the mass, so 15.0 grams, times the heat capacity. And this time we're dealing with water, so we use 4.18 joules per gram degrees C. And then we do our change in temperature, so our final is 35.0, and our initial is 0 degrees C. And so that, let's see, 15.0 times 4.18 times 35.0. And this one again should be 3 sig figs in the end, so I'll keep one extra. So 2195 joules is what that step comes out to. The grams cancel, the degrees C cancel. So that tells me the heat for each of those steps, okay? So that means for this step, that amount of heat is the 315 joules. And then the second one, that is the 5.011 kilojoules. And then this step is the 2195 joules. Okay, and so if I just add those together, that would tell me the heat for that entire process. Okay, and so I would take the 315 joules, I would add it to, let's see, we have 5.011 kilojoules, so really that's 5,011 joules. Okay, we need them in the same unit. And then add to the 2195 joules. Oops. Okay, so let's get back to this. And if we pay attention to our sig figs as well here, in the 315, the 5 is our last sig fig. In the 5011, it's really that first one because I had an extra sig fig there. And same with the 2195, really the 9 is where my sig figs end. So I'm going to end up rounding it to the tens place when I add these. And so I'm going to take 315 plus 5011 plus 2195, and that gives me 7521 joules. And so I'm going to round it to 7 point, sorry, not 7, maybe 7,520 joules, which you could also say, so you could say that, or 7.52 kilojoules, which I believe I thought I had copied the answer here, which, yeah, I've got, that's what I have as the solution, 7,520 joules. Okay, and so that's where that comes from, which, like I said, you could convert that to kilojoules if you wanted to. Okay, let's do at least a couple more, at least setting them up. So I might not go through and do all the calculations, but at least get it set up. So now, this next one says calculate the total amount of heat energy required to completely vaporize 3.50 grams of ice at negative 18 degrees C. Okay, and so this one I didn't give a heating curve. But we want to take this ice that's at negative 18 degrees C and we want to add enough heat until we eventually vaporize it. So what you have to realize is first, that ice, before it can be vaporized, it first needs to melt, and then it can be vaporized after some temperature changes as well. So we can't melt the ice until we take that 18 degrees C ice and we convert it to 0 degrees C ice, because that's the melting point. And then we can take our 0 degrees C ice, and as we add more heat, it melts. And so it becomes 0 degrees C water. And then next up, we have our 0 degrees C water. Oops. And as we add heat to the 0 degrees C water, it's going to heat up until it reaches its boiling point of 100 degrees C. So we heat it up to 100 degrees C water. And once we have 100 degrees C water, then we add more heat and we get 100 degrees C steam, okay, or gaseous water, if you want to say it that way. Okay, and that's what we want. We wanted to completely vaporize it. It doesn't say anything about raising the temperature anymore. Okay, so we'll stop at 100. And so really here we've got 4 steps. And so for those, you've got to calculate the temperature changes using heat capacities and the phase changes using enthalpies. So the first one's a temperature change. So I use the heat capacity of that substance. So I need the heat capacity of ice or solid water. Okay, and so I would take the mass of my sample, the 3.50 grams. I would multiply it by the heat capacity of the solid, 37.1 joules. Oh, and I actually, now that I look at the units, it's in moles. So that's a molar heat capacity. So we don't actually want the mass. I need to first convert that to moles. So I'm going to go ahead and squeeze that in there. So I want to get rid of the grams and go to moles. And since this is water, I use the molar mass of water, so 18.02 grams per mole. And then I'm going to use that molar heat capacity. Okay, so then I take times the change in temperature, which is the final 0 degrees C minus the initial negative 18 degrees C. And then you can calculate that. I'm going to go ahead and write out the work for these other steps. So we've got now a phase transition. We're going from ice to water. So I'm going to take my amount, the 3.50 grams, and I need the enthalpy of fusion, which is given here, and it's in kilojoules per mole. So I again need to convert this to moles. So it's that same conversion. So you could just do this off to the side and just use the number of moles in the calculation instead. Either way works. And then I multiply by the enthalpy, so the 6.01 kilojoules per mole. Okay, and then this next one's a temperature change, and I need the heat capacity for the liquid water. Okay, and since that again is given on a per mole basis, I'm going to take the 3.5 grams and convert it to moles. So again, if you don't want to rewrite that conversion every time, you could do that first and then just take those moles in the calculation. And then the heat capacity, the 75.3 joules per mole degrees C. And then times the change in temperature, so 100 degrees C minus 0 degrees C. And then the last step is a phase change. And so the phase change in this case is a vaporization, so I need the delta H of vaporization. And that is in kilojoules per mole. So again, I'm going to take the 3.50 grams and convert it, to moles. That's supposed to be 18.02 grams per mole. And then multiply it by the 40.67 kilojoules per mole. And so you'd calculate each one of those and then you'd add them together. You've got to be careful, pay attention to the units. So here grams cancels, moles cancels, degrees C cancels, and so you come out in joules, okay? And then this next one, grams cancels, moles cancels, but you come out in kilojoules for that step. And then the next one, grams cancels, moles cancels, degrees C cancels, and it comes out in joules. And then the last one comes out in kilojoules. So you can't just add the numbers that come directly out of those. You need to convert them either all to joules or all to kilojoules, then add them. But you can go through and do that and just, practice and then check. And you should get, after you do all of that, 16.8 kilojoules for that process, for the total, the sum of those results. Okay. Now let's set up at least one more. And so this next one, I've got a 29 gram sample of acetone, and it's heated from a solid at negative 94.8 degrees C to a liquid at negative 50 degrees C. and I want to know how much energy is required for this change. So this one's a little different in that I have a different sample, right? I have acetone instead of water. So for that one, I actually gave you the melting point because I said it starts as a solid and we bring it to a liquid. So it's important you know at what temperature do you have to stop your temperature calculation and do a phase transition calculation. Okay, and so that's what the melting point is telling you. Okay, for water, it's 0 degrees C for melting and 100 degrees C for boiling. But other substances, that's not what it is. Okay, so we know at 94.8 degrees C, or negative 94.8, that's our melting point. Meaning we actually start at the melting point, but it's a solid. Okay, so we have a sample at negative 94.8 degrees C, and it's a solid. Okay, so a solid at negative 94.8 degrees C, and we want to first convert it to a liquid, right, because it's at the melting point, and so we're going to add heat until we melt it. That's one step, and then we have this, we have this liquid at, there we go, at negative 94.8 degrees C, and as we add more heat, eventually we'll get to liquid that is at negative 50 degrees C. So that's our goal temperature, to raise it up to negative 50 degrees C. And so this one, we've got 2 steps we need to calculate, and then we would add those together. Okay, so again, I'll set up the calculation. And so the first one's a phase transition, and that is going from solid to liquid. So we need the enthalpy of fusion. And if you look at that, the units are in kilojoules per mole. So you can even start with that number if you wanted to. So 5.69 kilojoules per mole. And you could say, okay, well, I need to cancel out that moles. And so you can convert the mole portion to grams, and that is a molar mass. And then you can multiply by the grams if you want. And so you can fill in those numbers. Now, if that's confusing, you can write it like the regular equation, which I'll go ahead and do in case that, doesn't make sense to you. So remember, for a phase change, it's basically just Q equals N delta H. And so my moles I get from my grams. So I take my 29 grams and I need to convert that to moles. Now be careful, the last examples we were using water, so it was 18.02, but here I give you the molar mass, okay? And so we need to use that 58.01 grams per mole. And then we can multiply by 5.69 kilojoules per mole to get the energy associated with that phase transition. And then the next one is a temperature change. So we need the heat capacity. And since it's the liquid phase, we need the heat capacity of the liquid, which is what's given there. And so for that one, we're going to take the mass, so 29 grams. Okay, we're plugging this into our Q equals MC delta T equation, right, for a temperature change. So the 29 grams times the heat capacity, which is 2.15 joules per gram. And this one is listed as Kelvin, okay? But that temperature unit, it's associated with a temperature change. So we could write it as per Kelvin or per degrees C. So don't let that bother you that the temperature change is going to be negative 50 degrees C minus a negative 94.8 degrees C. Those degrees C are for a change, so it'll cancel that Kelvin. So if it makes you feel better, you could just change that unit and say that it's per degree C because that's equivalent in terms of a heat capacity. Okay, so you could go through and calculate that stuff, and again, you would then add those values together. And if you do that, let's see, what you should come up with is 5.64 kilojoules. And so I'll let you check that and make sure that that's what you get. So that should be, enough to kind of get you started in doing those types of calculations, calculating how much heat is associated with different temperature and phase transitions for a substance. And the heat capacities and enthalpies, those are values that you're typically either given or you have tables that you can look at a table of values and find those. And so you're not expected to just have them memorized.